Hello and namaskar. This is P.V. Sudarshan from the Department of Chemistry, St. Joseph Pre-University College, Bangalore. In today's session, I'll be dealing with thermodynamics and redox reaction. This session will strengthen you to deal with these topics in a better way. In fact, thermodynamics is a classical topic which deals with our day-to-day activity with scientific temper. As we try to discuss each question, let us understand the concept and the terms and definition which we have studied in our regular classes that would help us in learning this chapter in a better way. Let's begin now. The reactant stored in a thermos flask is an example of option A, open system, option B, closed system, option C, isolated system, option D, reversible reaction. First of all, let us understand what is the system. System is a part of a universe. System plus surrounding is equal to universe. System is categorized into three types. One is open system, closed system and isolated system. An open system is that where there is exchange of both matter and energy with the surrounding. A closed system is that where there is exchange of energy but not matter with the surrounding. An isolated system is that where there is neither exchange of matter nor energy with the surrounding. If you have understood the statements that I have made, you should be reeling with the answer. It is the reactant stored in a thermos flask belongs to an isolated system where there is neither exchange of heat nor matter with the surrounding. Therefore, the right option is option C, isolated system is the correct answer. Our next question, which of the following is or are examples of state function? Before I tell what is the answer here, let me give you a brief synapse of what exactly a state function is. A state function is a thermodynamic state of an equilibrium system irrespective of the path it is attained. The classical examples of state functions are mass, energy, free energy, entropy, the three basic thermodynamic physical quantities such as pressure, temperature, volume. Volume of water in a pond is again a very good example of a state function. Why is it so? The reason for that is the volume of water in a pond, it is irrespective of how the water has reached the pond. It could be due to rain, it could be due to a tube well, or it could be from any other source. From the examples that I have mentioned, you have the answer, I suppose, on the board. Examples of a state function, all forms of energy, mass, pressure, temperature, volume, density and plentiful. Therefore, if I tell what is the answer for this, answer is all of these: internal energy, enthalpy, entropy are examples of state functions. Next question, which of the following is not an example of a state function? In the previous question we discussed what could be the examples of a state function. Under that, I remember telling you all the three thermodynamic physical quantities: temperature, pressure, volume, all are examples of state function. In that, I have all the three mentioned here: option A, Pressure is a state function. Work I have not discussed, I will come back to it. Volume is a state function. Temperature is a state function. Then what about work? Work is said to be a path function. Then what is a path function? Or how do I give work as an example for a path function? Work is said to be done when a force is applied on an object to move it from one point to another point. It needs to describe the steps that are being involved in moving an object from one point to another point. It depends upon the number of parts or the number of relevant steps that are taking place. Therefore, work is an example of path function. It doesn't fit into the category called state function. The other example of a path function is heat and moles. Therefore, three examples for path function you need to remember: heat, work and moles. Whereas the three thermodynamic physical quantities which are commonly used are examples of state function. They are pressure, temperature, volume and most of the forms of energies under this. Therefore, coming back to my question, which of the following is not a state function? I would say the answer is option B. Work is not a state function, it is a path function. Next question. Internal energy of the system can undergo changes when? Option A, heat passes into or out of the system. Option B, work is done on or by the system. Option C, matter enters or leaves the system. And option D, all are true. Let's understand what is internal energy. You would have studied from the regular classes that internal energy is the summation of various forms of energy. The sum total of various forms of energy is defined as the internal energy. Due to so many energies taking part when a particle is in motion, there would definitely be changes in heat of the system. That is, whenever there are changes in the movement of the particles, internal energy definitely would have a significant role to play. Whenever heat passes into or out of the system, there would be a significant amount of internal energy changes taking place. Similarly, whenever work is done on the system or by the system, there is a change in the internal energy. And whenever matter enters or leaves the system, then also there are certainly changes taking place in the system. Therefore, the right option is option D, all are true, meaning whenever heat passes into or out of the system, whenever work is done on or by the system, whenever matter enters or leaves the system, there is a significant amount of internal changes taking place. Therefore, option D, all are true. Our next question. For the reaction N2 plus 3H2 giving 2NH3, all are in the gaseous state, the relation between delta H and delta U, that is the relation between enthalpy and internal energy, is option A, enthalpy change is equal to internal energy change, that is delta H is equal to delta U. Option B, delta H greater than delta U. Option C, delta H less than delta U. Option D, delta H plus delta U is equal to 0. To work this, we need to understand the relation between enthalpy and internal energy. The relation is, you should be aware, delta H is equal to delta U plus RT delta N, where delta N is the difference in the number of moles of the product which are there in the gaseous state minus the number of moles of the reactants which are there in the gaseous state. It is clearly visible from the above equation that number of moles of the products which are there in the gaseous state happens to be 2, while number of moles of the reactants which are there in the gaseous state happens to be 4. Therefore, I get delta N is equal to, it is 2 minus 4, which happens to be minus 2. Now from this, what do I infer is, if the number of moles of the gaseous products and the reactants that I have derived, that is from delta N. Delta N was number of moles of the gaseous products minus number of moles of the gaseous reactants. If it is a negative value, then delta H is certainly less than delta U. If delta N is a positive value, then delta H would be greater than delta U. If delta N is equal to 0, then by all probability delta H is equal to delta U. Summarizing what I mentioned, delta N will decide what is the relationship between delta H and delta U. Since delta N is a negative value, therefore I would say delta H would be less than delta U. Therefore, the correct and right answer is option C. Next question, which of the following conditions is valid for a spontaneous reaction? Now what is a spontaneous reaction? A reaction which can occur on its own with or without any external agency is said to be a spontaneous reaction. For example, zinc dropped in dilute HCl, hydrogen gas is liberated. It is a spontaneous reaction. There are necessary criteria and conditions for predicting whether the reaction is spontaneous or not. Remember two rhyming words: minimum energy, maximum entropy. And the third one, free energy change. These are the three deciding factors which can predict and tell whether the reaction is spontaneous or not. All those reactions in which delta H is negative, minimum energy, reactions are spontaneous. All those reactions in which entropy is positive, greater than 0, they are spontaneous. Free energy change, delta G, if it is negative, it is spontaneous. I mentioned about these two terms, entropy and free energy. What is this entropy? Entropy is a randomness of a system, disorderness of a system, while free energy is the amount of energy available to do useful work. So quickly summarizing, conditions necessary for a spontaneous reaction: delta H should be negative, delta S should be positive, delta G should be negative. Now here it's connected only with delta H and delta S. Let's look into the options. Option A is delta H is positive. I am ruling it out, though there are exceptional cases. Melting of ice, delta H is positive. It is a spontaneous process. Come back. Option B, delta H negative, less than 0. Delta S, entropy change greater than 0. Classical example or conditions are matching for this. Therefore, the right and the correct option is delta H less than 0, delta S greater than 0 is an example, are the condition for a reaction to be spontaneous. Again, few more reactions that would definitely help you. Entropy change increases in the order which you have studied earlier, solid to liquid to gas. I mean to say, in sublimation, entropy increases. In polymerization, entropy decreases. Do remember even these points. Our next question. If delta G naught for a reaction is 0, then its Kp value would be. It is a relation between delta G naught and Kp, standard free energy change and equilibrium constant with reference to pressure. This relation is known as Van 't Hoff reaction isotherm, and I am writing it. This relation is delta G naught is equal to minus 2.303 RT log of Kp. The question itself signifies and says that delta G naught is 0, understanding 0 divided by whatever I transfer it to the denominator here would definitely be 0. I will get log of Kp as it is. If I want to solve this, equate 0 in terms of log, therefore I will write log 1 is definitely 0, which is equal to log Kp. Log can get cancelled on either side. Therefore, the value of Kp is equal to 1. Therefore, the right answer is option B. 1 is the answer. Our next question. Bond dissociation enthalpies of hydrogen, chlorine and HCl are mentioned. The enthalpy of formation of HCl is. This is a question which has got bond dissociation enthalpies. You would have been quite familiar with delta H change is equal to heat of the products minus heat of the reactants. But here, when it is with regard to bond dissociation enthalpies, the formula is slightly altered. So, first let me write the enthalpy of formation of HCl. So, I write the equation H2 plus Cl2 is giving me HCl, you are aware. The enthalpy of formation of HCl, I will balance this, half H2, half Cl2 is giving me HCl. Now, in this, if I want to calculate what is the enthalpy change for this equation, should be aware that it is the summation of the bond dissociation of the reactants minus the summation of the bond dissociation of the products. Therefore, I will write the bond dissociation energy relevant to that of the reactants minus the summation of the bond dissociation enthalpies of that of the products. Let me complete by adding up the values for it. So, hydrogen, I understand enthalpy of hydrogen was given as 434, it is half of 434 plus it is half of enthalpy of that of chlorine is given as 242 minus enthalpy of that of HCl is given as 431. On solving this, I get it as 217 plus minus 431. Solving this further, I get the answer as minus 93 because the unit was designated as kilojoule per mole. Therefore, the right option is option C, minus 93 kilojoule per mole.